Hello everyone and welcome to the second video on a quick dive on machine learning. In today's video we will cover supervised learning. Supervised learning contains two types of models. You have classification models, which we will cover in a separate video, and regression models. Regression models are used to predict continuous values. So think about predicting the return of a stock, which is exactly the exercise that we will try to cover today, predicting handwriting. So it's really predicting continuous values. When you read about supervised learning, you're often presented with this kind of explanation. So you need to collect historical data and the data needs to be organized. What does that mean? So here you got your historical data, and the historical data contains attributes which are classified into labels. The model is there to establish this relationship here. The model that you choose, and there are a huge variety of models that you can select, that you can use, are there to establish relationships between attributes and labels. In other words, between inputs and outputs. When the model has done its job and it's learned something, can be then applied to predict future values or to predict labels with new data that has never been seen before. Now, this is what they write about supervised learning, which is absolutely correct, but let's look at a concrete example and what it means having organized data. So imagine we are collecting data for a security and we're looking at things like the ROE of the stock, we're looking at the price to book, we're looking at the PE, we're looking at the momentum of the security, and we can go on and on with the list of attributes. So these are attributes for one single stock. Now, we've seen earlier we need to have labels. What is a label? Well, a label can be anything and depends on the objective of the exercise. It depends on what you're trying to predict, what you're trying to estimate. But let's say that in this case, for instance, the label is the future 12-month return of a stock. So if today is time t, we're going to go forward in time, t plus 12 months, and we go to check what the return of the stock is. And we'll put our return right here. So you have the attributes, the inputs, and you have the outputs right here. So this is just for one example. So you need to go out and collect as much data as you can because the model will not be able to learn just from one simple example. So you go out, you collect a lot of attributes, you collect a lot of outputs, and this is really your historical data set. Now you need to select a model, that's the next step, and the model will sit right here in the middle. So let's call it NN, which stands for neural network. Now what the neural network will do is during a training phase, you need to select from the historical data some sample data, a data that you are happy to use, and then again it's very important that you're using data that is valuable. That if you will train, for example, a model during the financial crisis, you will be able to train the model on a very difficult period. If you train instead a model on a period where the market is moving on a straight line, again, it will be more difficult potentially for the network to learn more volatile periods. So you really need to have a hugely diversified data set that contains as much example as possible so that you can train the network very well. What I just said, it is true, although that may lead to unwanted problems. And the unwanted problem that you have is effectively trying to present too much diversified outputs, if you want, given the same inputs, in which case the network will not be able to learn anything. Imagine if you have two companies that have a very attractive momentum, let's say, but then the one company is performing well 12 months later and one company is performing very badly in the next period, the next year, whatever the time frame is. Obviously, you have two inputs that are identical and two outputs that are completely opposite to each other. That means that the network will not be able to predict anything, will not be able to learn from that example. So the quality of the data that you're using for training is essential. And so during the training, what happens is the network will, or the model in general, will try to establish a relationship between the given inputs and the outputs. If the model was trained successfully, then you can apply it to future data and you will be able to sort of get some meaningful results. But let's have a look at an example. The example that we prepared for this video is a neural network that is trained to predict the future returns of a stock. It's clearly a very difficult task, and before we look at this application, we have tried to test the model on a simpler exercise. The simpler exercise is trying to use a neural network to predict or to estimate better the moving average of a stock. Now, the moving average that we are trying to estimate is a 50-day moving average, which clearly requires 50 data points. Each data point is weighted by 2%, 1 over 50. So we will try to predict that with fewer inputs. Rather than relying just on prices, we also have 2 additional inputs that we would like to use. And that's the moving average over 5 days and the moving average over 20 days. So by taking the 5-day and 20-day moving average, we're trying to estimate the value of the 50-day moving average. So to do that, we loaded some data. We have taken Barclays as an example. We could have taken any other stock. Let's have a look at the share price of Barclays. Here it is in blue. We compute the 50-day moving average, which is our objective. It's the target. If you want, it's the labels that we are trying to predict with the model. Now, the inputs that we are using are the 5-day moving average and the 20-day moving average, which we're not displaying on this chart. Now that we have all the data, we need to choose the model that we want to train. We've decided to use a nonlinear autoregressive model with exogenous inputs, where the exogenous inputs are the 5-day and the 20-day moving average. And this specific type of model, or this specific type of neural network, being autoregressive means that the forecast that the model is doing are fed back into, as an input into the network. So there are a couple of things that we need to decide and fix before we can start training the model. The first thing is, for instance, the length of the data set. We decided to take 80% of this data set. We got data that goes from February 2002 till April 18. We've taken 80% of that for training, and we will be testing the result of the model, or we will be testing the model to see if it's able to predict in the following 20%. The other inputs that we need to put into the model, the other parameters that we need to fix, are the delays that we want to apply to the inputs we're using. We've taken from 1 to 4. That means the last 4 days, the last 4 observations are fed into the model. And then we've taken from 1 to 2 days the feedback of the forecast as input for the model. So you also need to specify the number of hidden layers that you have in the model, and then you're ready to train the neural network. Now, in the interest of time, we've trained the network already before, so we can start having a look at what the results are. And as you can see here, you have a perfect output. It's perfect in the sense that the 2 lines are overlapping each other. Now, if you zoom in, you will see that there is still a little gap. So you can see quite clearly that the blue line is the actual level of the 50-day moving average. The red line is the trained model, the output of the trained model. And so it's very, very close. Sometimes you can see here there is a delay in the response. So the moving average is turning. This is a turning point. And the network has sort of predicted with a minor delay. But overall, when you zoom out, you can see that the 2 lines are on top of each other. So the network has done its job and it learned something. But to be 100% sure that the network has learned something, we need to test it. So as I said earlier, we've taken 80% of the observation for training. That goes from February 2 till January 15. And then in the remaining data points, we're going to test the model and see if it predicts the moving average. So that's what we are doing right now. So we are simulating the following periods. The purple line is the prediction done by the model, and the black line instead is the actual level of the moving average. So overall, you can see that the model is able to estimate the moving average quite well. We would need to zoom in to see if there are very big errors and mistakes. And I'm interested, of course, to see if there are mistakes around the turning points, because this model can be used, for instance, for filtering a time series, trying to predict when the turning point of a time series occurs. And so it's very important to see how the model responds and behaves around the turning points. And you can see that actually the model has done quite well. In fact, here, in this point here, it has almost predicted ahead of time a turning point of the moving average over 50 days. And so if you zoom out, you can say overall that the network was able to understand how the calculation, if you want, of the 50-day moving average. Okay, so now we're ready to move to the second exercise, which is more exciting, clearly, and far more difficult, predicting future returns for a stock. So to do that, well, we're sticking to Barclays, so that's the stock that we're trying to predict. We're taking the returns. Now the inputs that we want to use are the historical 5-day returns. So it's a sequence of the previous 5-day returns to predict tomorrow's return. You need to select, you need to put in a couple of parameters for the model. In this case, we've decided to fix to 10 the number of hidden layers, neurons in the layer, and you can play with that number. You can make it much larger, and the network will be able to learn more accurately the historical data, but that will lead to instability in the results when you go testing, and we will show you what we mean by that. So in the interest of time, we have saved already a network already, so it's already saved and trained, so we are importing that now here. And let's see what the prediction was. So you can notice right away that compared to the moving average exercise, the network here wasn't really able to fit all data points. But the ultimate goal is not necessarily to have a perfect fit. You need to have a model that has been trained, has learned something, and it's able to predict something. Predicting perfectly what's going to happen tomorrow, it's impossible. It's a task that you cannot do. But if you are on average able to get an indication of where the direction of the stock may be tomorrow in the next days, that could be a very useful information that can be used for trading. So what you can see here is that the network has done something very simple. It has favored some spikes. So for instance, in this period here, we can zoom in, you can see that it was able to fit this big drop in the returns of Barclays when the day when the stock was down just over 7%. The network, which in this case is the blue line, was able to fit that point very, very well. And equally, other points where it spiked, like in this area, you could see that the model was able to fit those spikes very well. The model failed, if you want, to predict more the average numbers, the numbers within the small percentage returns. But that's not really a big problem. So in order to judge if the work that we did is good, if the training was successful, we need to go out and test it on fresh data, on data that the network hasn't seen yet. So we are going to go out and test in the remaining days the network, and we go to measure the performance of this model. So here are the results. Now what you see on the left hand side is the same chart that we saw earlier. So the training sets, blue is what the model produced, red is the actual data. So the top chart on the right hand side, you see really the testing results. So we've been testing the model from February 18 till April 18, so it's a relatively long period without retraining the network. So the forecast, you can see some similarity from the training exercise. As I said earlier, the network doesn't seem to be able to predict very well the sort of small movements. In fact, here you can see that the network has produced basically zero returns when the stock was bouncing around, and instead it shoots out and predicts some little spikes. So Again, it's very difficult to understand from this picture if you're able to use in trading or if this information can help you in taking a view on the stock. So the first natural thing to do is to translate those expected returns into a forecast, into a price forecast. So you can see here the blue line is the price of Barclays that we predicted, and the red line is what Barclays did. Clearly, there is a very big gap, so we can't say that the network did a very good job. But again, is it really the price that we want to predict, or are we trying to use the network to get indication regarding market directions and take a view on that? Well, the outcome, when you look at the trading strategy that is trading the stock, that is buying the stock if the prediction of a positive return occurs, and goes short the stock instead if a negative return is expected, you see the chart at the bottom here, and the results is quite encouraging. You know, the red line is the performance of Barclays over this period, which was just under 5%, and instead the model that we trained has produced in excess of 20% over that period of time. So even though the prediction as such wasn't great, so the training wasn't ideal, you can see there the error is still was very big. The predictions of returns in the testing area, again, there were a lot of errors in the predictions. Clearly, when you look at the price projections, again, you can't see a perfect prediction of future prices. But when you put that into a trading model, you can see that the network has actually been able to come up with some successful ideas. The takeaways for regression models within supervised learning are the following. First of all, over the past years, computer power has increased enormously, and that enables you to train in a very rapid and in a very accurate way. Complicated models just 10 years ago would have taken a long time to train. So it is true, today you could perform tasks that you were not able to perform in the past. However, a model will be able to learn what can be learned, in the sense that you need to be able to train a model on data that's got an impact on the output. And we can look at an example. If we try to predict the return of a stock tomorrow, we need to be able to, with a model, we need to be able to train that model with inputs that are actually affecting the return of a stock. It is impossible to try to predict tomorrow's return with inputs that may be logical but have no impact whatsoever on the behavior of a stock. And that is the most challenging problem. So predicting what happens tomorrow is incredibly difficult. And the example that we've seen today, we show that it is very difficult to train a model in a very good way without entering into the problem of overfitting. You could get some good outcomes. But the problem is, and this is the other problem of neural networks, is you don't know when the outcome is reliable or not reliable. Because after the training, and you can assess if the training happened in a good way, we know what kind of data the model is seeing, you understand, have you trained it using highly volatile periods or lowly volatile periods? We can assess all that information. We can see the results of the training phase, but then when we go out and test the model, well, the model will always produce an outcome, will always produce the forecast, will tell you, well, tomorrow the stock is going to go up or down. But the model is not able to tell you, I'm confident 100% about my forecast. You don't have an element, an indication on how reliable that outcome is. And I'm afraid the only way to do it, the only way to try to understand how reliable the forecast is to assess the historical performance of the model. That's the only way that you can get an understanding on the reliability of that data. And so, and whenever you retrain a model with newer data sets, you know, it may forget things that it learned in the past, and it may stop working well in the future. So relying exclusively on neural networks or regression models in general for predicting the market is very, very dangerous. The final problem that we believe you have, and we have with neural networks is the problem of overfitting. You can clearly, by expanding the size of the problem, you will be able to fit the data in a perfect way, in a very accurate way. And sometimes it's astonishing to see how well a network can learn from historical data, but then when you put it into production on future data, you see that the results are completely random and they're not really very good. So again, there is no right or wrong, and I'm afraid there are no solutions for these problems. One needs to spend a lot of time with these models to understand how they behave in practice. But the most important takeaway is really neural networks regression models in general, are effectively big equations that are fitted to data that you're feeding to the system. And they will always be trained, they can always be trained, and they can always be tested. But in order to rely on the models, you really need to try to, let's say, predict or estimate something that is predictable, something that is tangible. Asking what the top news of a newspaper will be tomorrow is impossible. It's something that you cannot predict. So what neural networks do very well, they can classify very well situations. Predicting what will happen tomorrow is a very complicated task. So although we looked at an example where we're trying to predict what happens tomorrow, we believe that possibly neural networks can be successfully used to create, for instance, filters of a time series, because predictions are very difficult to make. Thank you very much for watching, and goodbye.